Hello everybody, welcome to 9.3 Part B, and what we're going to talk about with the rest of Chapter 9.3 are sums. And we're going to talk about finite sequences and their sums, and we're also going to talk about infinite series and those sums, and lastly we're going to apply this stuff to real-life applications. So to begin, what we're going to do is talk about sums of finite geometric sequences. So the sum of a finite geometric sequence. Okay. And so what we're going to do here is we're going to label this S sub n, right? Because we've talked before about how S sub n represents sums, and we're going to represent this two ways just so we can recognize it a couple of ways. It could look like a sigma notation with some value n on top, right, because it's finite, it ends. And we could say I equals 1 on the bottom, and then we'd have a sub I times r to the I minus 1. And I want you to recognize that this is actually a geometric sequence right here, right, with an a sub 1 times a ratio to the n minus 1. That is very similar. And what this is equal to, in and of itself, is the formula a sub 1 times 1 minus r to the n over 1 minus r. So let's use both pieces of information to get through an example. Let's say we were asked to find the sum sigma 12 on top, n equals 1 on bottom, of the formula function 4 times 0.3 to the n. What I want you to realize about this question is it's actually giving you a few pieces of information. This matches this right here, where we have an a sub I, and we have a ratio, 0.3, and we have that to the n. So again, 0.3 would be our ratio here, and the 4 would sort of be like our a sub I, just the number we're multiplying by in front. And so what we can do with that info is we can use this to set up the formula here that's a little bit easier to work with. To begin, we need to put in the first term. We can find the first term of this sequence by substituting in a 1 for n, right? 1 means it'll be the first term. So when I do that, I get 4 outside 0.3, right? That's just the first term. And then I can say 1 minus the ratio, which we found was 0.3, to the n. The n value that we're stopping at is 12, so that's where I'm filling that in. And I have it all over 1 minus the r value, 1 minus 0.3. And that's really it. I do want to reiterate, though, what everything is here and why it's there. 4 times 0.3 was our a sub 1 value. 0.3 to the 12 was our r to the n. And 0.3 was just the r. That's where all the pieces fit in. And when I simplify that out in my calculator, I find that it's approximately 1.714 when I round to 3 places. Now, let's talk about when things get a little bit different. When we're talking not about finite geometric sequences, but infinite. So, the next topic is geometric series. And in parentheses, I'm going to write the word infinite just so we don't forget that that's what we're dealing with here. Okay. Geometric series, and we're talking about infinite things. Basically, what we're going to have is two scenarios for a geometric series. The first is that our r value, right, normally we could have a sigma with an infinity, right? And we could say n equals 1, and we could have some a sub I, and then we could have an r to the I minus 1. What I want to illustrate here is that, this should be I, not n. what I want to illustrate here is as I approaches infinity, we're going to have either two cases. We're going to have either the case where r is less than 1 or where r is greater than 1. And two very distinct things are going to happen. When r is less than 1, what we can kind of imagine happening there is, for example, just a little example for yourself, a fraction, right? Something less than 1 would be a fraction. So let's imagine maybe 1/2. And then instead of thinking I minus 1, let's think honestly about approaching infinity. Let's think about 1/2 with a really, really, really big exponent. Obviously, I can't evaluate infinity. I can't just throw that into a calculator. But I can think about really big numbers. I can think about 1/2 approaching a really, really big exponent number. And if you use your calculator to do this, or if you just kind of think about it in your head, what happens when I multiply two fractions together is the denominators get bigger. And right here, if the denominator of this gets very, 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 very large, I actually get a number that approaches 0. So I'm going to write a little arrow here and 0. Conversely, when I have a number that's greater than 1, let's say, for example, in this case, I had 2. Let's say my ratio was 2, and I was trying to see what would happen as I plug in bigger and bigger values into its exponent. This one is a little bit simpler to imagine. I mean, imagine making this just a bigger and bigger and bigger and bigger number. What it's going to approach is infinity. And so what that means is, when r is greater than 1, it won't have a sum. Because if I was to substitute this in for the r to the n piece in my formula, everything would just be getting close to infinity, right? Putting a really big number on top of a fraction isn't going to make it change at all. It's just going to be infinity, and it's not going to have any sort of sum we can kind of see happening. However, what happens here with the r less than 1 is, say I had that formula S sub n, right? And I wanted to see what's kind of happening. 1 minus r to the n over 1 minus r. That's our formula, right? But now what we're interested in seeing is when as n approaches infinity, right? So S sub infinity, a sub 1, 1 minus, and here's what we talked about. We know that when r is less than 1, right? When the ratio is less than 1, this piece right here, r to the n, gets really, really small and approaches 0. And I have that over 1 minus r still. So this, in short, becomes 1 over 1 minus r, and if I multiply a sub 1 by that, I get a sub 1 over 1 minus r. And that is the formula that we use when we're talking about infinite series, this right here. And this is the reasoning as to why, right? Again, this only applies when the ratio is less than 1. When it's greater than 1, it won't have a sum when we're talking about infinite series. Okay, let's do an example of this, just to kind of prove some points here. So let's say we were asked to find the sum sigma. Let's say we had an infinity on top and we had n equals 1, and we had in front 4 times 0.6 to the n minus 1. What I can recognize here is that what I'm going to have is 0.6 as my ratio. And using that, let's set up our formula. So our formula says to do a sub 1, so that means I'm throwing a 1 in here for n. I'm doing 4 times 0.6 to the 1 minus 1 all over 1 minus r, 1 minus 0.6. When I simplify some things, 1 minus 1 is 0, and 0.6 to the 0 power is just 1. So I get 4 over 0.4, right? 1 minus 0.6 is 0.4. When I divide that out, I get the answer 10, and that's my answer. Let's say, for example, I was given the task to find the sum of the following series written out. 0.3, 3 is the first term, 3 plus 0.3 plus 0.03 plus 0.003, and then we have plus ... What I want to do first here to kind of help you visualize what's happening is to write out this just a little bit differently. This is the same as saying 3 plus 3 times 0.1 plus 3 times 0.1 squared plus 3 times 0.1 cubed, ... And so we can see from this pattern what our ratio appears to be is this 0.1. And using that and using our formula, we can go ahead and set up our formula. We know a sub 1 goes on top, and a sub 1 in this case is 3. And on the bottom we have 1 minus our ratio, 1 minus 0.1. When I simplify this out, I get 3 over 0.9, and when I simplify that, I could kind of multiply both top and bottom by 10. When I do that, I get 30 over 9, and now this is pretty easy to simplify. I know 3 goes into 30 10 times, and 3 goes into 9 3 times, which gets me approximately 3.33 repeating. Okay, let's do an example of this, kind of trying to apply it back to our more realistic application. Okay. Alright, so I have written out this problem. If you want to pause the video to copy it all down, go for it. I'm just going to start reading it and we'll start solving it. So a deposit of $50 is made on the first day of each month in a savings account that pays 6% compounded monthly. What is the balance at the end of 2 years? So what this question is asking us to do is add together all of the compounded $50 that were made in the course of 2 years. But what's important to keep in mind is that each deposit would be compounded for a little bit less, right? A little bit less time. So here's what I also want to remind you of. Compounded monthly, remember that formula. We have A equals P, initial amount, outside 1 plus the rate over the number of compoundings plus the number of compoundings times the time in years. So that's really going to be what we're going to use to set things up for ourselves today. First though, like I said, each deposit is going to be compounded just a little bit differently. So let's talk about the first deposit. The first deposit made in these accounts, we can call that A sub 24, right? Because it's going to get 24 months worth of interest compounded to it. And that we can represent as 50, right? The amount deposited. And then we have 1 plus the rate, which is 0.06, over the number of compoundings, which would be 12 because it's monthly. And then right here, we'd have 12 for the 2 years. So 12 times 2 should get us a 24 out here. And then what we're going to be doing is, and that really also represents like the 24 months of compounding that that's going to go through. So similarly, when we're talking about the second deposit, now we're no longer talking for 24 months. That's come and that's gone. That was our first deposit for the first month, and now that month is gone forever. Now we only have 23 months left. So we're evaluating with a 23 as our exponent this time. And what's important to understand about that is that that's going to be a pattern that's going to stick with this whole problem. The third deposit would be a 22. The fourth deposit would be a 21, right? Because the months are going to keep going by, and it's not going to be compounded for as long every time we deposit something in. I also want to simplify some stuff out here. For the first deposit, when we add 1 plus 0.06 over 12, what we end up getting in there is a 1.005 to the 24. And over here, similarly, we get 50 outside 1.005 to the 23, and so on and so forth. And what we can do is we kind of can do dot, 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 right? Continuing and so forth. We can conclude that the last deposit they're going to make, if we keep on with this trend, the last one is only going to have 1 month of interest. So we're going to have A sub 1, last amount, is going to be 50 outside that same 1.005. This inner piece never changes. We still have the same rate and the same number of months in our compounding. But on the outside, it's only going to be compounded for 1 month. Okay. And so we have 50 times 1.005. And now we actually have every piece that we need to fill in for our S sub n formula. What we can call this right here, the first deposit made, is actually going to be the R sub n value. And here, the last deposit made, we're going to call that our A sub 1 value. And keeping all that in mind, we're going to set up our formula. So, S sub n equals 50 outside 1.005, and that's all outside of, I guess I should use a bracket there, not parentheses. There we go. 1 minus parentheses 1.005 to the 24th, all over 1 minus 1.005. And when you simplify that all out and put it all together in your calculator, what you get is 1,277.96. And that is the resulting value of all those deposits added up. That's the balance at the end of the 2 years. Okay, thanks for watching. We'll see you in class tomorrow.